All right, so somebody else asked me about a problem involving a cuboid, which can just be a little intimidating if you haven't dealt with them before. So our cuboid has the wonderful name A B C D E F G H, and it's a cuboid, so that means it's a rectangular prism. There's always 90-degree angles between each of the edges there, and we're given that B is. I'm actually going to try to graph this out. So let's make that straight up and down. So we're given B is 320. So you go 3 steps over and then 2 steps this way. So right here, B, 320. C is 231. So we'll go 2 steps, 1, 2, 3 steps, 1 step up. So I know it kind of looks like it's on the y axis. It's not. Just gotta use your imagination to see that that was actually 2 steps X, 3 steps Y, and then 1 step Z. It just visually is going to coincide with the axis there. D is 1, 1, 2. So 1 step, 2 steps up. So it's going to be right about here. And then G is 0, 3, -1. 0, 0, 3, -1. Okay. Okay, so how the heck does this make a cuboid? That's really weird looking. I was expecting there to be a little more regularity in those dimensions. Let me double check that I copied it right. Yeah, that's weird. Okay. Interesting. Okay, well, maybe my picture is going to be too hard to draw, but what I know when I'm drawing a cuboid in general is that A, B, C, D are going to be along one face, and then they're going to connect to sort of what we can call the backside of it, A, B, C, D, and then we can connect that along the backside to E, F, G, and H like that. So I guess we have enough information to figure out, for example, what coordinate A would be. And the way we can do that is if you look at BC, for example, the vector that goes from B to C goes from B is at 320 and C is at 231. So we can say 2 minus 3 for the x values, 3 minus 2 for the y values, and 1 minus 0. What I did is I took the C coordinates and I subtracted the B coordinates. And this tells me that to move from B to C in that direction means I had to take one away from X, add one to Y, add one to Z. And so that means that if I want to do the same thing, A to D is going to be the same vector because they're moving in the same direction. If I wanted to move from D to A, then what I know is it's just the opposite direction. 1, -1, -1. So what I can do is I know the coordinates of D. D equals 1, 1, 2. And so that this implies that A is going to equal 1 plus 1, 1 minus 1, and 2 minus 1. How did I know that? I took the coordinates of D and I applied dA to it. So this 1 plus 1, this 1 minus 1, this 2 minus 1 right there leads me to coordinates A. I could have done the same thing if I had found what CD's vector is and done the same thing with BA. So that's a good double check. I'm going to double check that I did that correctly. If I look at CD's vector, that's going from C to D. So I go D minus C, D minus C, D minus C. And I get -1, -2, 1. That turns out to be pointing in the same direction as BA. So if I take B's coordinates of 3, 2, 0, then that implies A's coordinates should be 3 minus 1, 2 minus 2, 0 plus 1. So it checks out. So now I have the value of A. And we can try to add that to my graph, even though my graph is just looking a little confusing to me. 2, 0, 1. 2, 0, 1. There's A. Okay, so I think, yeah, so this is my front of my cuboid, and then it extends, let's see, C extends to G, so it extends backwards like that. Okay, good. Now I need to find the length of a space diagonal. So the length of a space diagonal would be going from either A to G, or from B to H, or from C to E. There's several different space diagonals. I'm just going to do A to G because I have both of those coordinates. So from A to G means we take G's coordinates and we subtract A's. So G minus A, G minus A, G minus A gives me -2, 3, -2. So then if we find the length of that, we're going to basically just use the distance formula. The length of AG is just the square root -2 squared plus 3 squared plus -2 squared. So 4 plus 4 plus 9, 17. Yeah, it's the square root of 17. Excuse me. Now to find the volume of the cuboid, we can just do our length times width times height. So I guess I could do AB. I want to use values that I know. So CG, CD, and CB would give me those. So let's do that in different color. To find the volume, let's do a different color. I am just going to do the length of CD times CB times CG, because that will give me vertical, horizontal, depth. Okay, so let's see. We already found CD here. We already found CB here. We just need to find CG and do its lengths. So let's do that over on the side first. So CG, do it up here. So CG means we're going to go G minus C. So what do we got? 0 minus 2, 3 minus 3, -1 minus 1, -2, 0, -2. Okay, so down here, when we're doing the volume, I'm just going to be applying the square root on each of those distance formulas. Square root, square root, square root. So for CD, it's going to be 1 plus 4 plus 1, because I just did -1 squared, -2 squared, +1 squared. For BC, it's just 1 plus 1 plus 1. Boom, boom, boom. For CG, it's 4 plus 0 plus 4. Right here, right here, right here. So the volume becomes square root of 9 times square root of 3 times square root of 8. So that's 3 times square root of 24, which you could reduce down because it's got square root of 4 in it if you want. So you can make that 6 times the square root of 6, because I pulled the square root of 4 out, leaving with the square root of 6, and that's the volume. So there you go. That's finding stuff out about a cuboid. My actual 3D graph wasn't so good, but that was okay because I was able to abstract the info just by looking at the coordinates of the vectors anyway. And this picture here in the middle was the mental image I have of a cuboid. So please comment. Let me know if I made a mistake. Very possible I messed up my numbers at some point, but that's the general idea.